decision I got to make. So. No, they'll both be the morning.
Let's just say
15%.
So Friday is off the table. Friday is out of it.
Friday is, no. Yeah, was the decision that wasn't up to me. So.
So this is all different. Any of these items.
Yeah, the game's on. Yeah, what's your question? No, oh, so date. That's fine. So when you look at the index, is that in our review?
This is like
Yeah.
Use the top section.
So basically, since these are all keys, they already all have indexes. And so PID is just, matching up. And since there's all white players all over, all of them are going to have a white player, so you don't necessarily need an index there. But to get dates, so you can just look for that one date faster, having an index for date is useful because it gets this one there. Because this one, you're going to have PIDs whites the whole way through. So you're just looking, but.
Alright, morning everybody. So a couple announcements. First, Elion is still looking for study participants. So it sounded like there was a couple people that signed up, but she was hoping to grab some more. Again, it's an hour, you get paid for it, and it should be pretty interesting. So I encourage you to volunteer. Suresh asked for feedback on his lecture, is the wrong word, but on Tuesday's class. So he's teaching a course in the fall called the Ethics of Data Science, and he wanted some feedback on how you guys felt about what we did Tuesday. So I appreciate if you sent me any thoughts that you had about that. The Kevin Bacon Lab due today. The Work 6 due tomorrow. Final exams both next Thursday. One at 7:30, one at 10. And then we're out of here for a few weeks. So. Huh? Yeah. Yeah. That's the university schedule. Yeah. If you're confident that you know the material, maybe you show up at 8:30. So that was a decision that was not made by me. Sucks for me too. I don't want to be here either. But the flip side of that is it's only one day, and then you have like 2.5 weeks off. So.
But is yours at 10 and other one? I mean, is it the same order, or do we?
I need to decide that with Varun. Yeah. Cool. So yeah, we're getting real close to the end. So today we're going to do some exam review that was requested, and then we'll talk a little bit more formally about what we have been looking at with interactive visualization with D3. So we'll talk about kind of the principles behind what we've been doing. And then on Tuesday and Wednesday next week, we'll look at a couple more sort of case studies in that area. And we'll play with some 3D graphic stuff too. So, cool. Any questions on any of that stuff before we jump into review? All right. Cool. So, there's kind of three major topics we've talked about since the midterm. We talked about dimensionality reduction. So we looked at both PCA and autoencoders for doing that. We looked at neural nets a bunch and basically saw how we could use those for most of the tasks that we had kind of seen other single purpose techniques for. And then we've been talking about interactive visualization stuff. So maybe we'll start with talking about PCA first. What's kind of the big idea behind PCA? Yeah, so we have data in high dimensions, many dimensions, and we'd like to represent that with fewer dimensions somehow. Yeah, PCA was one technique for dimensionality reduction. Why would we want to do dimensionality reduction? What benefits are there?
Reduce the number of dimensions, make calculations less costly.
So we could do it for some sort of efficiency reasons. So if I have a 100-dimensional data set that I want to do clustering on or classification or something, those algorithms might be really slow if I have 100 dimensions. Right? If I want to do KNN and I have 100D data, right? My queries might be really slow. But if I reduce the dimension down, right, those tasks might become more efficient. So that's one application. Why else might we want to do dimensionality reduction? Denoise. Yeah, we could use it for denoising. So the information we lose when we do dimensionality reduction, hopefully, is the information that's not so important. Assuming we do the reduction in a smart way. Yeah, for visualization, right? I can visualize 2, maybe 3 dimensions. That's about it, right? PCA lets us, or dimensionality reduction can give us a way to get something that we can visualize. Cool. So, what was kind of the key idea behind PCA? So, how did it work as a way of dimensionality reduction? I have some data here. And how does PCA, what did it give me that reduced the dimensionality of this?
Like just the data on a certain plane or hyperplane, that data fits on.
Yeah, that's pretty close. Anybody want to try to explain it another way?
Remove the dimension that has less variation along.
Exactly. Yeah. So we're looking for the directions of maximum variation. So in this case, that would be along this direction, right? And then and we're doing this repeatedly where each subsequent direction, right, is perpendicular to all the others. And so for this one, I have 2D data, right? So my two PCA axes would be, these two axes. Okay. I still have two axes here. How did this reduce the dimension? Okay. So my points, before they had an X and a Y coordinate, now they have, let's call these A and B coordinates. So I took my XY representation, I now have an AB representation. How is that useful?
So we just not have a dimension.
So the A dimension contains most of the information about my points. So if I just don't store the B and assume that all the B coordinates are 0, then I have reduced the dimensions. Instead of storing an X and Y, I just store an A. Okay? And so I have reduced the dimension of my data. So it's kind of nice, right? If I wanted to do like a KNN kind of thing here, right? If I have XY data, I have to use some clever spatial partitioning data structure. If I have my dimensional reduced data, I just sort it. Right? I have 1D data, I just sort it. I just made my task a lot easier. Right. If I have a coordinate that's A, and I just have the A value, how do I reconstruct its XY? What information do I need to have to do that? So really all I need to know is basically what is my A direction in terms of X and Y. Right, so I have to know, in terms of my XY coordinates, which way does my A direction point? Right, and then I basically take the A value and multiply by that. And that's the. So if I have my point starts out as XY. That's the same as taking my however far along the A axis I am times the A axis plus however far along the B axis I am times the direction of the B axis, right? And these are in terms of my original XY. Then I can reconstruct. So when I do dimensionality reduction, right, I just assume that some of these terms are 0, right? So I reduce the amount of data I store and introduce a little bit of error. But hopefully it's a little bit of error. Cool. Questions about how PCA works, what it's useful for? So in terms of finding these, what these axes are, we looked at the math for that a little bit. Right? We want to maximize the variation along whatever the direction we're looking for. We can also think of this whole process as trying to rotate my axes so that they align with the data as best as possible. Or you can think of it as trying to fit an ellipse around my data, and the axes of that ellipse are also the same. The principal components, the directions of maximum variation. Yeah.
Will this be like the last exam as far as the amount of math that we need to know?
Yeah, it'll be probably pretty similar. Yeah. Yeah. So I'm not going to ask you for equations about this stuff, but I am going to ask how to use it. Cool. So what are the limitations of PCA? Why isn't this the only dimensionality reduction tool? It's linear, right? It only works along lines, right? So if I had data that looked like this, I tried to run PCA on it, I'd get, something weird and useless, right? This is essentially one-dimensional data, right? All the points are along this line, but PCA can't talk about, this curve. Right? So I need some sort of way of describing this curve and like where I am on the curve. Anybody have any guesses on how you might do that? Have we seen a similar problem before? So the same thing we did with SVMs when we wanted to put a flat slice between things that weren't necessarily separated by a flat slice. We warped the space until it was flat. We can actually do similar stuff here. It's called kernel PCA, where you add in an extra function that handles this like kind of curvature stuff. So that's one approach you can use to that for that. But yeah, you can use. There's a whole Wikipedia page on the kernel trick, which is like common for anytime you want to use one of these kind of linear methods on data that's curved. You can try using a kernel trick to kind of warp stuff. Cool. So that's PCA. Any other questions on that? All right. The next thing we talked about for a couple weeks was neural networks. So what's kind of the fundamental unit of the neural network? A layer is a collection of neurons or perceptrons, right? So if we think of a perceptron as like a functional unit thing, what happens in here? What's the guts of a neuron? So I have my inputs. I have my bias, the input that's always fixed to 1. Cool. And what do I do with my inputs? I weight them, so I multiply them. By some weight. All right. Got my weighted inputs. What do I do with them? I'm not done with them yet. So how many outputs come out of a single neuron? So each neuron only has one output. Right? So somehow I have to go from all of these to a single output. So the first thing I do is I just add them all together. And then I have to stick them through an activation function, and then I get my output. So without the activation function, so let me remember what we're doing.
So that's linear regression.
Yeah, so if I don't do the activation function, this is just linear regression written in a really complicated way. And we actually saw an example where we did linear regression, we used a neural network with no activation function, and we saw that they gave the exact same results. So the activation function smushes my output some way so that basically I can represent more complex things than my output. So what were some of the activation functions we talked about?
Ignoring.
So the ReLU and the sigmoid. Okay. Anybody remember any others? Linear, so none. Yep, that's an easy one. Yeah, step function. There's one other. I don't know that we actually used it. Maybe we did. It was closely related to the sigmoid. Called the tanh, the hyperbolic tangent. And And it's very similar to the sigmoid. So we'll start with a step function. What does that look like? All right, we're off and then we're on. Okay. And how about these other ones? Cool. So the ReLU, basically, if it's negative, we set it to 0. Otherwise, we leave it alone. And then the sigmoid or the hyperbolic tangent. These are just smooth versions of the step function. And the difference between these two is basically like where the axis is. The sigmoid goes from 0 to 1. The hyperbolic tangent, I believe, goes from -1 to 1. Okay. So this is a single neuron. Usually we group them into layers. So within a layer, we don't connect any of the neurons in a layer together, right? But they have connections to the previous layer and the layer after. All right. So how do we go about training a neural network? So I run some inputs through. I have my my input layer. I have whatever neurons in my network in the middle, and then I have an output layer.
When you compare the output with what you expect the output should be, you see what the error is, and then you back propagate and change all the weights and stuff.
Yeah, so I have examples, training examples where I have inputs and I know what the output should be, which means neural nets are what kind of learning algorithm? Supervised, right? Because I have outputs that I know what they should be. Okay. So I run my examples through. I see how well I did. I see what mistakes I made, and then I update the weights a little bit to reduce the error. Okay. Then I just do this a bunch of times. So it's called gradient descent is the common term. So the gradient tells me how I can change my weights a little bit to minimize the error a little bit. And, a little bit being infinitesimally small. We don't have time for that, so we used finite amounts of change. But that's the basic approach. And there's some tweaks to that so that we don't get stuck in local minima and things like that. But the basic idea is we look at how to change the weights to reduce the error a little bit. Cool. So questions on the basics of the neural networks? So if I wanted to use this for regression, what would my network look like? So what is a regression problem? It's kind of one of the, I don't know that we actually looked at using neural nets for this, but it was one of the first things we did. So, so what would the shape of my network be if I'm doing regression? Or what are some aspects of the shape? Is there a limit on the inputs I can have? So let's think about like other regression. So let's think about regressions we've done without a neural network. So what types of things what types of problems did we try to solve with regression? Sure. So what types of problems do we try to solve with linear regression?
Like prediction.
Prediction. So give me a concrete example.
I think we looked at newspapers, for advertising newspapers.
Yeah, we tried to predict sales based on how much we spent on advertising. Cool. Yeah. So for that, we had, was there a limit on the number of inputs we could have?
There wasn't a limit, but you wanted to adjust your readers, I believe, to ensure that they were all significant.
Okay. So I could have whatever inputs I want, right? You know, it just depends on how many features I have data for, right? And then how many outputs do I have? Just one, right? Just the value I'm predicting, right? So if I wanted to use a neural network for prediction or for regression, right? It would look something like that. What if I wanted to use it as a classifier? What would it look like? So the inputs, is the size of the input still, you know, whatever data I have? Yep, so whatever, you know, however many inputs I have, whatever. And the outputs, right, I'm going to have one output per class, right? And what does that output tell me?
Probability factor.
So the output per class is going to tell me the probability that my input is from that class. To do that, we're actually probably going to use one of these guys, and then we're going to, on top of that, we're going to use the softmax function that just like normalizes all the outputs so that they add up to 1. Cool. What about an autoencoder? Yep. So what's my shape going to be?
Hourglass.
So my input and output are going to be the same. And probably in the middle, I'm going to have a lower dimensional layer than my input and output. Okay. And so I could, why would I want to use an autoencoder? I could use it for denoising. You looked at one other. Yeah, dimensionality reduction, compression. Why would I want to use an autoencoder for dimensionality reduction instead of maybe like PCA?
You have to reserve the orange note information.
Well, with PCA, I hopefully could reconstruct the original as well. What advantages are an autoencoder going to give me? Yeah, the autoencoder, since it's a neural network, I can fit any sort of crazy shapes to my data that I want. Right? So I'm not restricted to linear stuff. My reduced dimensional coordinates can be an arbitrary function of the inputs, basically. Right? Do all sorts of crazy stuff. Cool. So these were kind of the basic. These are all the feed-forward neural networks. What does it mean for it to be feed-forward? Yeah, I go from my input layer through my hidden layers to my output, and there's no like loops or anything like that. Cool. If I want to do looping, what techniques do we talk about for that? So if I wanted, if I want my, one prediction to impact the next prediction, then I would use a recurrent neural network, the RNN, and the the recurrent neuron has some information stored inside of it called the hidden state. And when we feed in data, we feed in an input, we change that hidden state, and we output something that depends on both my input and my hidden state. Okay. And that's, so the neurons have memory and history associated with them. So we saw how we could use these for like text prediction. We played around with the char RNN. So when we're dealing with sequence type data, this can be really useful. We also talked a little bit about the more complicated version. So this was a recurrent neuron. There was a more complicated recurrent neuron that we talked about a little bit. Remember what that was called? Yeah, it is long short-term memory, LSTMs. What was like what was the key idea there? What did the LSTMs get us? Yeah, so LSTMs gave us a little bit finer grained control over what we remember and what we forget. So there's the update, how the hidden state gets updated was a little bit more complicated, so we could kind of explicitly remember or forget stuff. And then the last type of neural network that we talked about was the convolutional neural network, the CNN. What was the deal there? Yeah, so we use these convolutional filters. So we have this little patch with weights, right? And we basically slide this over the image, right? And we get, and we just take the activation function of our little filter dot product with the patch, so just multiply and sum it up. And this was one of our convolutional filters. So why did we bother with these?
So that we have fewer ways to.
We wanted to reduce the number of weights to train, and how did this help us with that?
Can I identify patterns?
Yep, so these weights are going to be like, they're going to look like kind of the patterns we're trying to detect. But how do these reduce the number of weights that we have to train? And so even if we had the same number of weights, maybe this would be useful because it's something we can sort of understand about the image, right? But this also makes it a lot easier to train these networks. So why does this give me fewer weights than if I just had my input and then a dense layer?
There's one output for every 9
It is actually probably usually increases. Typically, we increase the size of our the convolutional layers. Usually, the output is a higher dimension than the input, actually, because we have a whole bunch of these.
So we group them like 3 by 3 layers. So we have 9 input pixels as one group, 9.
Yes, but remember, we apply these. I'm going to apply it to this little section, and then this section, and then this section. So I'm actually going to, overlap these, and so I'm not actually reducing the output dimension of this layer. I'm applying these to each little patch in the image. So where does the weight savings come from? The pooling reduces the dimension. So pooling, is like downscaling. But there's no weights associated with that. So if there's a bunch of weights here, then where do we save on weights? Not necessarily. I have fewer weights that I have to train if I use convolution layers. So I have a whole bunch of outputs, but my output weights are not independent. Right? These 9 weights are going to be used to generate outputs at every pixel in the whole image. Right? So I might have 1 million outputs. If I have a 1 megapixel input, I'll have 1 million outputs from this layer, but I only have 9 weights to train. So these weights are reused across the whole image. Right? These filters are applied to the whole image. Right? So I only have a small number of weights that produce a big number of outputs. Right? If I have a dense layer here, right, every neuron here has a connection to all 1 million pixels here. Right? So I have a ton of weights here. In this case, I have 1 million input pixels, only 9 weights, and 1 million output pixels. Does that make sense? So we're reusing the weights across the image, right? And that's why these are easier to train, is because we're reducing the number of weights. We're probably increasing the dimension because we probably are fitting a whole bunch of these filters. So in the examples we saw, we fit 32 or 64 or whatever, right? So we went from grayscale at every pixel to 64 dimensions at every pixel. So we increased our data by a lot, but we were only training 64 times 9 weights. Questions about that? So that's the key idea. We're reusing the weights across the image, and that's what gives us makes it easier to train, is because we have fewer weights.
Yeah, sorry, it's still not clear to me. When would you select this over an RNN?
So an RNN would be when we need some sort of history as part of this, where the data comes in like a time series, or like in order. It's kind of the typical case. Another reason you'd want the RNN is because you don't know how many inputs or outputs you're going to have. Right? So if you're doing like machine translation, right, you don't know how long of a sentence somebody's going to ask you to translate. You don't know how many words it's going to be to output. Right? And so the RNN lets you do it one thing at a time. The convolution layer, there's no sort of time. So I could think of an image as ordered in terms of like the pixels, like their position. So you could imagine using like an RNN to go through the picture like row by row or something. If you're doing image classification, probably you just want to look at like the image as a whole in one shot. Other questions on CNNs? Cool. The only other neural network thing, we talked a little bit about dropouts. Does anyone remember what dropout is? So when we're training with dropout, we basically just turn off some neurons during some training steps. Right? Seems pretty dumb. Like your hardware is broken. Right? What was the purpose of dropout?
Isn't it to force the other neurons to kind of? Isn't it kind of adds a little bit of randomization?
Mm-hmm. Like that. Yep. So we pick which ones are turned off randomly. And yeah, we're basically trying to spread the load. So it has the effect of kind of reducing the average weights, right? Because if I have one neuron with a really high weight, with really high weights in it, and I turn it off, it's going to have a big impact on the output. My output's probably going to have a lot more error when I turn that neuron off, right? And so I'm going to have to like crank up the rest of the neurons to pick up the slack, right? And so it's like kind of a load balancer, and another term is regularization. It can help with overfitting as well. It helps with training, avoid overfitting and all that stuff.
Do we also like reduce the sensitivity to the input data?
Yeah. Mm-hmm. So, well, yeah, I would say, so if you didn't have dropout, you could have a few neurons that are like really active with high weights that might be really sensitive to the input data. And so dropout would kind of spread that effect out. So it might reduce the sensitivity to kind of outliers. Cool. So any other neural network questions? Since it's due tomorrow, I assume some of you are pretty close to the end of the assignment on it. Has anybody found out anything kind of interesting from playing with the font classification stuff? So what happened? So when you trained on one font and tested on another, what did people see? Did it work at all, or?
Not initially.
Okay. What kind of like accuracy comparisons do you have? Like, so I train on Courier, test on Courier versus train on Courier, test on like Times New Roman or something.
I went from like 45% to like 30%.
Okay, so 45 to 30. So pretty big drop, but still much better than guessing, right?
Yeah, mine was like really low.
Depends on the font you use.
Yeah, it depends on the font. Yeah.
The biggest single thing that seemed to affect accuracy was how many inputs were expected, how many different characters there were. I was trying to guess.
Yep. So the dimensionality output, whether the like some of the fonts they had like all those sorts of weird like almost X's, right? Yeah, it's going to be hard to tell all those apart with the limited training data that we have, right? It's not a huge data set, so yeah, kind of to be expected with all that weird Unicode stuff in there that might have some issues. If we were, any thoughts on how we could maybe try to deal with issues kind of like that? Adjust our problem a little bit to
Reduce the data set just like operating characters.
So we could exclude all the weird characters. What else could we do?
I don't know that this would work in all cases, but maybe we scale a little bit differently, so kind of like chopping off portions of it.
So if I chop off this, so I'm changing my X, like what about the label that's associated with it?
I guess it would just depend if you want your labels to be the same.
Well, so if I chop off the tilde and I expect to get the label of Unicode X with tilde or whatever, then I'm making the problem a lot harder, right? What could I do to the label? One thing I do is just say all of these are capital X, and then that might work really well because we're kind of introducing a little bit of noise into our training data, right? So if we, if our testing data, is a little bit different from our training data, adding this noise in training might help, right? Because we kind of learn the model was trained to deal with slight variations. So that might be another approach we could play with. How about the training with 2 fonts stuff? How did that work out?
My training with 2 fonts and testing out third actually performed better, but that's because I went from 2 fonts that had a really high number of characters to one that was quite low, so it shrunk them all. I think that's what proved it.
Okay. What about the accuracy just on the 2 training fonts? How did that compare to like training on 1?
My accuracy went down by about 10%.
So it was a harder to do that. Another thing you could add another output for the prediction of which font it is. So you can have the add one more output dimension being, is it font A or font B? And see if the network can recognize not only which letter, but which font it came from. Cool. Did if somebody asks you to build a neural network to do some sort of classifier or something, would you be confident with how to start?
Well,
Start, yeah.
Yes. Import carrots. Yeah. Do you have more confidence than you did 2 weeks ago?
Yeah.
Okay. Okay. Cool. So that's neural net. Any other questions on neural net stuff? Next thing we talked about was graphs. So we talked about a little bit about how we can store graph data. We kind of talked about 2 kind of data structures we might use for that. Do you remember?
The adjacency list and matrix.
So either do kind of like a node or edge centric thing, where we store with each node the edges coming out of it, for example, or we can store an adjacency matrix where we have either weights or just true or false corresponding to whether there's an edge between a pair of nodes. We talked about some analysis, some things we might want to measure, compute about graphs. So what are some of the things we looked at there? We talked about degrees. So what does the degree mean?
Incoming edges.
So the degree is the number of edges. For an undirected graph, it's pretty straightforward. If we have a directed graph, we have to be a little bit more careful. What would be interested in for a directed graph? So be interested in the in degree or the out degree, probably. Cool. What else do we look at? Talked about finding paths, so searching, shortest paths, that kind of stuff. All right. We talked about some sort of related quantities that we can compute, kind of related to paths. One was pretty weird sounding, and the other you use every day. PageRank, right? Which, if you were going to describe PageRank in 2 words, to a layperson, like why they should care about it, it's the Google algorithm. PageRank is the Google algorithm. What does it measure? Or where does it come from? It's related to connectedness.
How likely are you to end up on that page from another page?
So we have a random graph traverser guy that starts at a node and he randomly follows edges forever, and PageRank tells us the probability of him ending up at a particular node in the graph. Okay. It gives us kind of a measure of importance right? If a random surfer is likely to end up at a particular page, that page is probably important. What Google uses that information for is to order their search rankings. Right? So they have an index of all the pages related to keywords, right? And they use PageRank to decide what order to show, the pages that contain whatever. I taught a scientific computing class a few years ago, and one of the projects, we took the NumPy documentation and indexed it and built the graph structure out of all the links and ran PageRank on it. And as you can imagine, right, the home page is like the highest PageRank hit. You can kind of see, and the array is kind of the next one, and all this sort of stuff. So it's very practical, pretty cool algorithm. So PageRank, we use that all the time. It's kind of a little bit more abstract and weird. And then there was another kind of per node measure related to paths that we talked about. The betweenness centrality. And what did that measure?
Is that, I don't know if it's the right one, but it's the PHP of the node, you had to go through that particular node.
Mm-hmm. Yeah, so we compute it's called the all pairs shortest paths. So we compute the shortest path from each node to every other node. Okay. And then the betweenness centrality is the percentage of those that go through a particular node. So we have like a star-shaped graph. The betweenness centrality of the thing in the middle is going to be 1 because every path goes through it. Right? If we had some other topology, right, it would be lower. Okay. So those were some of the things we looked at. We talked about graph visualization. What were the kind of 3 sort of general visualization types we talked about? Do you remember? First one is like the obvious one. Nodes and edges, so that's the node link diagram, where we just draw nodes and edges as, some sort of a symbol for a node, some sort of line or curve for an edge. Okay. So that's kind of the standard one, most obvious one. What were the other 2 we talked about? Talked about the matrix, so we could do like a pixel display of the adjacency matrix. And the third one only worked for trees. So that was the containment. So instead of drawing edges, we draw children inside of their parent. So we saw that for like a grand perspective. It shows you your disk space usage. Right? The things inside of a folder are drawn inside of a folder, inside of the space, right? And then we could have this hierarchical picture. Right. So the purpose of the visualizations is always to answer some sort of question. Right? So there's 2 sort of families of tasks that we talked about. I remember what those were. Talked about attribute-based or topology-based. So what were some, anybody remember any of the attribute-based tasks? So these would be things that like depend on edge weights, stuff like that. So maybe the average edge weight or the maximum edge weight or something. The topology-based tasks depended on things like connectivity. I think we talked more about kind of the topology-based stuff. So some of the topology-based tasks would be things like finding a clique. Which visualization would be best for clique finding, potentially, if you do it right? The matrix, right? So how would you spot a clique in a matrix representation? It's a big old block all filled in, right? If what? If you have ordered your rows and columns so that the clique ones are actually next to each other. And so the matrix is great for that if you have ordered your rows well. If I wanted to look at shortest paths, what representation would I want to use? Node link. The matrix is pretty bad for shortest paths. How come? Yeah, the path edges are actually not connected in the matrix. Right? You'll be jumping through the matrix, seemingly randomly for paths. So if you're interested in paths and that kind of stuff, then the node link is probably the way to go. For the node link one, when we want to draw them, right, we have to pick where to put the nodes. It can be pretty hard. What are some of the considerations we have when we lay out a node link diagram? So what would we like for those to do with those distances?
Oh, this thing less similar, farther.
Yeah. So in general, we probably want edges to be relatively uniformly length, unless we have a reason for otherwise. What's the biggest consideration we have in laying these out? Kind of the number one goal, and probably the most difficult of them to actually achieve. I'm looking at a node link diagram. What's like the worst thing for me when I'm trying to understand it? So hairballing, we have too many edges or too many nodes. We have to do something about that.
Edges crossing.
Yeah, minimizing edge crossings is probably the most important. Right? And it's also an intractably hard computational problem, so sucks. But that's life. In general, right, we can't. Most graphs, there have to be some crossings, but minimizing that is really hard. We want symmetry, so similar things should look similar. We might, so there's a whole bunch of criteria we talked about that are all kind of in conflict all the time. So how did we go about actually laying out nodes? What are some of the things we actually did? So one thing we did was we let physics kind of do it for us. So those are the force-directed graph layouts. So we charged all of our nodes, so they repel everything, and then we connected springs to pull things that were connected together. And, so those actually work reasonably well. What were some of the pros of the force-directed layouts? Yeah, it does make pretty good use of space. Yeah. So you could interact with it. That might be a good thing. what does it do with things like clicks and clusters? Yeah, so the springs will pull clusters together, so it's pretty good for seeing clusters. What are some of the cons? Yeah, so it's, unless you have the same initial conditions, which typically you kind of randomize the initial positions, you'll get a different output each time. So if you lay the same graph out twice, you'll get 2 different visualizations. And so if you're doing like some sort of editing as you go, you're not going to get anything consistent between layouts, right? And so it's, you can't rely on previous visualizations to kind of orient yourself. Another problem is it's relatively slow. So to converge to get some, so stuff's going to be moving around and then it's going to kind of slow down. If that ever happens, right, it can take a while to get there. It may never happen. Things might kind of oscillate back and forth forever, which not ideal. Right. What other layouts do we talk about? Kind of 2 others. So one, we talked about a constrained layout. So for example, putting stuff around a circle. Right? That way, the edge placement is, or the node placement is, could be, we can make it consistent between layouts, right, if we're editing the graph or something. If we have a good ordering for how stuff goes around the circle, we can might make it easier to spot patterns. Especially if we use edge bundling, right, we can cut down on hairball looking stuff. What was the last layout we looked at? Didn't work for all data sets. Just look at it for the submarine cable map. Sometimes the nodes actually have position associated with them, so we just use that. So if we have like geographic data, we just put the nodes where the nodes are. Right. So that may or may not be helpful. Right? We talked about how we might use the submarine cable data, or why you might want to visualize it in a different way. But our tools were too primitive to do a good job of that. We talked about why we don't want to do that. Cool. Any other graph visualization, graph analysis questions? All right. On Tuesday, we talked about sort of responsible data science. Right? So what are some of the questions that we should be asking when we're doing data science, trying to solve data science problems? Yeah, who are the stakeholders who's going to be impacted?
How the data was obtained.
Yeah, where does the data come from? Right. The first question we had was, what is the question I'm trying to answer? Right? How do we define, what it is we're trying to answer? So, what does it mean to? What is misinformation, or what does it mean to improve policing or reduce crime? So those are some of the questions that we need to ask when we're doing real-world data science. And then with the rest of today, and then on Tuesday and Wednesday next week, we're going to look more at interactive visualization. So we played around with some D3 last week, and we're going to kind of talk about some of the fundamental principles that we kind of maybe had some intuition about, but we'll talk about them a little bit more formally. So, in addition, I'd say flip through the midterm. So some of those questions and topics will pop up again. Any other exam review questions? Yeah.
What extent should we know the interactive visualization if we're doing a JavaScript stuff?
You shouldn't need to write code. We'll talk probably more about principles. All right, cool. So we saw playing with the Kevin Bacon data sets, or the movie data set, even the Kevin Bacon subset of that data, that the data set is kind of too big for us to see all of it in a single visualization, in a single static visualization, right? When we tried to do a node link diagram, we got just a hairball, right? And so one of the approaches to make a data set like that visualizable is to allow the user, the viewer, to interact with it, right? So that they can produce kind of the views they need as they need them, right? Instead of trying to show everything all at once. Okay. So we're going to talk about, today I think we'll talk more about manipulating a single view, and then on Tuesday we'll talk about why you would want multiple views at the same time. These are both, ways of showing part of the data at a time and allowing the user to sort of control what's shown when. In order to the functionality that we need to add for the user, there's a few things. So we're going to talk about change of view, so changing what view we have of the data. Selection, which is important to change, to sort of navigate or change what is shown based on user input. We'll talk about navigation, so how a user can sort of move through our data set, and also attribute reduction, so how they can control which, for a given group of data points, how they can control which features of the data are shown. So we'll start with change of view. So we kind of did this in a sort of clunky way once we started playing with Jupyter Notebooks and Matplotlib. But oftentimes we have a view of the data, and that leads us to want to see a different view of the data. So for example, maybe we start by looking at a histogram of some data, and based on what we see in the histogram, we need to see a scatter plot of the data, or a histogram of a subset of the data. There's kind of two changes of view that are pretty common. So one is we might want to change the encoding. Right. So changing what our marks and channels are. So this could be going from a bar chart to a line chart, or a histogram to a box and whisker plot, or whatever else. Right. Another task we might, or another interaction we might want, is reordering or sorting elements. Right. So both of these are, if you played with Excel, you do both these things all the time, right? You sort your table by different columns or whatever, and you can make different charts, that visualize your data using different encodings. We want to give the user the power to do these changes of view, right? As they're exploring the data, their understanding of what they want to look at and how they want to see it, right, is going to change. And so this is a feature that we want to add. If we are changing, depending on how sort of dramatic or drastic the change is, it might be really, really helpful to have an animated transition between the views. Right? What would, aside from looking pretty, what value does animation provide for us in terms of understanding?
Show like same data moving across space, or
yeah. So how would that help us understand it better?
I guess some parts of the relations might be maintained, like one set of animation to the other.
Exactly. So we want to connect the old view and the new view, and an animated transition can help us with that, right? So we can see like, oh, this section of the data, it did look like this, now it looks like this, right? Whereas if we just the textbook uses the term jump cut, right? So you're doing video editing and you just stop one and immediately start another video, right? There's no context. There's no. You have to reorient yourself once you see the new view, right? And so an animation can allow us to use what we've noticed or seen from the previous view and understand this new view with that context. Right? When we're changing the view in our little Kevin Bacon visualizer, how might animated transitions help with what we're looking at? Having elements fade in and out could have been useful, so that we can kind of see like, oh, this node is going away, these edges are going away, as opposed to like, oh, they're gone. Right? So it can give us the cue as to what's changing and how. Cool. So changing views is important, right? And if we can change the views smoothly, then we can preserve sort of the context in our head as it changes. The next thing we'll need for interaction where we can change views typically is some sort of mechanism for selection of data. So if I wanted to, zoom in at particular elements or get extra information about some elements or compute something based on, some set of the data, the user needs to be able to select those elements. Okay? So some questions that will depend on the application that you need to answer are, which elements can be selected? Does it make sense to select multiple items at the same time? Does it make sense to select 0 things? So may or may not. Can you select things by group easily, or is it one at a time kind of thing? And can you select things based on attributes? Right? So for our Kevin Bacon data, maybe it makes sense to be able to select all the movies from the 80s, right? Would like a clicking on nodes based selection be a good interface for doing that? Probably not, right? We'd need some other mechanism for the user to select, based on these attributes. So we might have direct selection. We might have some sort of indirect selection where we specify, like, here's the things that I want. And so that's so selection can be a complicated thing. So for our node link diagram, selecting the 80s movies would be pretty tough to do. Is there another view of the data that might make it easy to do that?
Seems like a histogram.
Yeah, so some sort of visualization where things are laid out by time. So yeah, maybe like a timeline, or you could have a histogram where you like you click on the histogram bar and you select all the movies in that time. Okay. So yeah, depending on what needs to be selected, right? These are all sort of important considerations. Right. The next thing we want for manipulating the view is to actually change the viewpoint of the viewer. Okay. Kind of the most straightforward thing to do is to treat kind of the viewer as the cameraman holding the camera and let them move in a kind of physical way, right? So if they can zoom out, they can pan, they can move around to explore the area. If you have 3D data, maybe they can rotate or they can move, arbitrarily in 3D. Although that's, you probably want, you don't want total freeform 3D movement. But these are, they map, they're pretty, you can interact, in a pretty physically analogous way, right? We can move stuff around. People kind of understand those idioms because they do them all the time in the real world. But we're actually not restricted to those interactions. We can perform semantic navigation, where we can do things that don't necessarily correspond to what's in the real world. Right? An example of that is semantic zooming, where as you zoom out, the representation of objects might change. Right? So maybe you have a visualization of like text files, and if you zoom in, maybe you see like the first line or so of the text in a document, and as you zoom out, maybe you see the title. And as you zoom really far out, maybe you just see squiggles, and there's nothing specific to that document that you can even see. Okay? So we have sort of infinite control over what happens as we zoom and move, and so we can use that in ways that don't necessarily correspond to the physical real world we're in. And can actually make it easier to navigate or give us more detail when it's needed and hide clutter when it's not. If we have, say, 3D data, right? Having unconstrained 3D navigation is probably a really bad idea. Are there any video games that people play where you have unconstrained 3D navigation ability.
Minecraft kind of just auto-generates more and more.
But the movement through Minecraft, is it constrained in any way? What constraints are there?
Up and down.
So up, the up direction is fixed. And that is a good, probably a good thing, right? Because if you could spin this way, you'd get disoriented really fast. And it's really hard to navigate in totally unconstrained 3D environments. Okay? Usually we want to add some sort of constraint to the motion that we can have. So if I'm looking at a picture of the Earth, right? What constraints might I have in how you navigate? So you might restrict how you rotate so that north is always facing up. Does it make sense to translate? Probably not, right? So how would you actually move around? So you'd want to rotate around like the center of the Earth or something, right? So that's a common thing, right? If you have a data set, you like keep the center of the data fixed, right? And then you can rotate around it as opposed to like translating. So that works for kind of like spherical data, or more like rectangular or boxy data. Maybe that makes less sense. But probably having some constraints in how you can move around is a good idea. The only games I can think of that where you have totally unconstrained motion would be some sort of like flying game. Anything where you're like walking around, right? The up is going to be kind of fixed, right? And you can probably translate or rotate, but usually the up direction is fixed. Okay. And then the last thing I will talk about today is attribute reduction. And this is where I have this data with more features than I want. And so I want to throw some of it away. And two techniques we can look at there are clipping or slicing. Clipping or slicing. So slicing is essentially, you can think of it as dimensionality reduction. So one example would be you have a CT scan, which is a 3D data set that has I don't know, like density or some sort of material information at every point in 3D space. If you want to look at the inside of that data set, it's kind of hard, right? I have a CT scan, right? I see the ribs or whatever, and I want to look at something inside of my chest cavity, right? I either need some sort of transparency, and then I have to ignore the parts that don't matter, or something. So one thing we can do is slice the data, and I can look at basically a 2D picture along a particular slice. So that's one approach. It's sort of a dimensionality reduction thing where I'm throwing away everything that's not on a particular plane that's going through data. Another thing I can do is clip or cut my data. So I say only draw the stuff below this plane, and then I can so I throw away everything on one half, right? So maybe I put a cut right through my chest cavity, and I see I can look down into what's in there, but everything that's above the plane is not. Those types of techniques really work well only in conjunction with interaction, right? If I can only have like a fixed, like, oh, I guess I'm going to cut right through here. If I want to look at something up here, then I'm out of luck, right? So I need to be able to change the view to adjust, where I'm clipping or slicing, so that I can navigate through my data. So those are just some of the ways that we can manipulate a view. We can change what data is being displayed. We can change the encoding. We can change our viewpoint. We can eliminate data points or attributes of the data based on what we need to see, right? And so that's how we can manage a large data set by changing, by manipulating what we're viewing over time. So we played with a few of those things last week with the D3, right? So what were some of the some manipulations and stuff that we had access to? Pretty limited, but so we could select actors to display. Right? That was kind of the biggest thing, right? And our selection directly impacted what we viewed. We had a little bit of like direct manipulation of placement of the actors. We could drag stuff around, but yeah, kind of the biggest thing was controlling what data was visible. We sort of skirted the issue of panning and zooming. So zooming would be probably a good thing to add, especially as we add more and more data. The panning would kind of also would probably make more sense when we're looking at larger parts of the graph. For the small samples we were looking at, right, the centering force that kept everything in the middle kind of kept us from needing to pan too much, but as our data got larger, pan and zoom would be important things to add. Cool. Any other questions on view manipulation? All right, cool. Enjoy your weekend, and I'll see you on Tuesday.